This is our first lab measuring constant velocity. The purpose of the lab was to analyze real-world versus computational characteristics of constant velocity with these three main objectives of observing an object's position in real life, predicting that object's movement in the simulation, and discussing the differences. We use VPython, a real-world marker and rolling, and excels in graphs, and use the knowledge of momentum principle from Newton's second law and the position update formula. Also that if the object moves at a constant velocity, that means its Fnet equals 0. The observed object moves positions a little less over time than the predicted computational result, and I'm going to take you into why that is. So this is the initial knowledge that I came in to the lab with. Starting with Newton's second law, defines a force equal to the change in momentum, which is mass times velocity per change in time. So if that velocity is constant, that mass that mass will be the only constant acting on it, which means that Fnet will be 0. I adapted Newton's second law into final velocity equals initial velocity plus Fnet times the mass of the ball times delta t for the lab, as well as the position update formula to get those data points that we can visually compare using the final position equals the initial position plus the velocity times delta t. So here, getting into the experiment and computation of the lab, the system was the marker and the surroundings were the air and the table. My hand doesn't really count as a surrounding because I was measuring it after I let go of the marker. So I took the marker and rolled it from left to right on my tabletop, trying to make it go at a constant velocity. I took that video and put it into Tracker to get the position of the marker over the span of less than 2 seconds. I put those into an Excel sheet and found the slope of the position to get the velocity of the marker and took that initial time and initial position as well. I took that initial position, that slope, constant velocity, the change in the initial time, and the delta t, which is 0.033, which is the frame rate of Tracker, as well as the knowledge that if it's moving at a constant velocity, the Fnet will be 0, and plug that all into my duplicate of the starter code. I put those equations I derived earlier into the code as well, so that when it runs through the while loop, the position of the ball simulation will update over time. Finally, I checked and made sure the simulation was good, and then I took all of those data points and started formulating my results. So I had the observed data points from Tracker as well as the data points from the simulation and put those into Excel and put them in a conjoined scatter plot to visually compare the data. You can see that the predicted position is this yellow dotted line and dots, and the observed is this orange one right underneath it. So the observed will be a little bit less because of air resistance, friction on the table, or human error, whether or not I have the ability to make something move and it at an exact constant velocity is a challenge. If I analyze my video in Tracker and made a different choice in the orientation of the axis, my overall results would be the same. My data points would just, say I move my axes from this side of the camera to this side of the screen here on the right, I would just be moving in the negative x direction towards the origin instead of in the positive x direction. So is there an instant in time where the net force equals 0 in case of the observed? I think there is like an instant or two or maybe a few instances where the force acting on the marker from my hand initially and the friction of the table and the air resistance make the Fnet equal 0, but I'm not sure when exactly that is, and based on the results, I couldn't really say for sure. But I think that there is an instant in time where the Fnet is 0, but I know it's probably not for the entirety of the lab since the friction of the table and the air resistance will make the marker's acceleration or velocity decrease over time. And all right, that's all I had. Thank you guys.